String time crystals. Presentation for the annual Time Waiver and Healy Scientific Advisory Board Conference, September 2024. By Dr. Hovdank Tadeus. String time crystals and Bose-Einstein condensates as a new state of matter involves three parts: holistic string time crystals theory, string time Bose-Einstein condensates matter, and string time crystals and Bose-Einstein condensate for therapeutic application in quantum feedback. The core concept in holistic string time crystals theory is that Bose-Einstein condensate, as a large-scale quantum field, activates strings' vibration modes which correspond to crystals. The collective quantum nature in Bose-Einstein condensate might allow it to serve as a large-scale quantum field, through which the strings' vibrations are effectively activated or enhanced, which enables the strings to resonate at frequencies that correspond to particles or states that exhibit time crystalline behavior, where the Hopf bifurcation acts as both the initiator and sustainer of the periodic oscillations. String time crystals. The interplay between string theory and time crystals delves into the assumption that string vibrations could mirror periodic time patterns, akin to those observed in time crystals. This proposal seeks to broaden the traditional particle-focused view of string vibrations, integrating an understanding of intrinsic temporal periodicity. This foundational research could inform further studies across various domains, including Bose-Einstein condensates and their applications in bioresonance therapy. So to begin with, what are time crystals? Time crystals are a state of matter that exhibit periodic changes in their quantum state, breaking time translation symmetry, which means they repeat their structure in time instead of space. While conventional crystals have a repeating spatial arrangement, time crystals show a pattern that oscillates at regular intervals. These oscillations can occur without energy input in a closed system, or they can be driven by an external periodic force in an open system, where the oscillations occur at subharmonic frequencies relative to the driving force. Let's delve into why time crystals are considered a new phase of matter. Unlike traditional phases, time crystals are unique because they can exist in two distinct dynamic states. One is the time crystal phase, where the system shows regular oscillations over time. The other is a stationary phase, where the system remains static, showing no change. This dual ability, this bistable nature, allows time crystals to switch between these two states. This switching depends on external conditions, like changes in driving frequency or coupling strength. The switching behavior observed in time crystals often arises from a bifurcation in the system's parameters, where the system transitions between two distinct phases. This transition takes place at a specific point known as the tricritical point. At this critical juncture, the system's nature changes fundamentally, shifting between dynamic states. In the time crystal phase, the system displays unique quantum characteristics, with atoms and light fields becoming collectively entangled, showcasing the non-equilibrium and dynamic nature of this phase. This entanglement highlights the complex interplay between quantum states and periodic temporal oscillations. Subharmonic frequencies in time crystals are integer fractions of the external driving frequency, reflecting broken temporal symmetry. This creates a stable, repeating pattern resistant to disturbances, maintained by the system's quantum coherence and interactions, highlighting time crystals' unique ability to remain in a non-equilibrium state. Time crystals and quantum tunneling both highlight unique behaviors in quantum mechanics, centered around non-equilibrium states, coherence, and symmetry breaking. While time crystals break time translation symmetry to sustain periodic oscillations, quantum tunneling allows particles to pass through spatial barriers that are otherwise impenetrable by classical physics. Exploring these connections enhances our understanding of quantum systems, where stability, transitions, and coherence define the behavior of matter at its smallest scales. Simulations show time crystals can form and stay stable in a 3D lattice of classical spins, where each spin only interacts with nearby ones through short-range connections, which serve as an analog to commonly investigated quantum spin chains, for example, qubits on a quantum processor. Theoretical models often use effective Hamiltonians to describe the behavior of time crystals, capturing the essential dynamics of the system under periodic driving without the complexity of the full Hamiltonian read. For high driving frequencies bottom, the effective Hamiltonian blue accurately describes the quantum dynamics of the atoms, aligning with how simplified models can effectively capture the core behaviors of time crystals. The dynamics of a particle on a vibrating mirror, particularly in subharmonic resonances where the particle oscillates at a fraction of the driving frequency, mirror the subharmonic responses seen in time crystals. By studying these resonances, researchers gain insight into the conditions that allow time crystals to sustain their periodic state and how external driving forces can induce time translation symmetry breaking. The dynamics of a particle on a vibrating mirror, particularly in subharmonic resonances where the particle oscillates at a fraction of the driving frequency, mirror the subharmonic responses seen in time crystals. By studying these resonances, researchers gain insight into the conditions that allow time crystals to sustain their periodic state and how external driving forces can induce time translation symmetry breaking. Let's now look at the string time crystals order Hamiltonian as an example. In this equation, we have the Hamiltonian H evaluated at the bifurcation point B, with energy fluctuations represented by a random log normal distribution. The term J is an imaginary number, used here to capture oscillatory or rotational components of the system, while temperature fluctuations are modeled by a normal distribution, phi t. The order of the system is captured by another random log normal distribution. This equation helps us understand how energy and order behave at critical points in string time crystal dynamics. Moving on to the quadratic oscillator, this is a generalized model for nonlinear oscillators, extended to consider up to 26 dimensions. This can be used to describe systems that don't exhibit bifurcation behavior. Here, R represents random elements, C refers to capacitive elements within the system, I stands for fields, and U represents the potential of these fields. This model helps explore how higher dimensional oscillators behave without undergoing bifurcation. Bifurcations play a crucial role in the behavior of time crystals. They mark the transition between distinct temporal phases within the system, showing how time translation symmetry is broken. This breaking of symmetry enables time crystals to exhibit multiple periodic behaviors, or temporal orders, depending on the external conditions, such as changes in the driving fields. These bifurcations are essential for understanding the nonlinear dynamics at play. In time crystals, even small changes in system parameters can lead to significant shifts in their oscillatory behavior. This phenomenon highlights the sensitivity and complexity of time crystals, helping us understand how they can remain stable yet adaptable under varying conditions. Bifurcation theory helps us understand how time crystals transition between stable and unstable states as system parameters change. This reveals the shifts in their behaviors over time. Nonlinear dynamics is crucial for studying how time crystals evolve, particularly when exposed to external influences, leading to multiple oscillatory modes. To model these changes, numerical simulations capture bifurcation points and the system's responses to external forces, providing detailed insights. Finally, dynamical systems theory gives us the mathematical tools to analyze how time crystals' periodic behaviors change with varying parameters. Hopf bifurcation in time crystals is the process by which a system transitions from a non-oscillatory, stationary state to a stable, oscillatory state as parameters are varied, marking the onset of time crystalline behavior. This bifurcation is crucial for understanding how time crystals form and maintain their periodic temporal order, highlighting the interplay between stability, symmetry breaking, and dynamic oscillations in these unique phases of matter. Temporal symmetry breaking. Hopf bifurcation specifically deals with the breaking of time translation symmetry, which is key to time crystals. It transitions the system into a state where it exhibits time periodic behavior, unlike static bifurcations that alter spatial configurations. Non-equilibrium dynamics. This bifurcation is tied to systems that are inherently non-equilibrium, leading to sustained oscillations. Complex eigenvalues. In Hopf bifurcation, the system's eigenvalues become complex conjugates, which is a hallmark of oscillatory motion, in contrast to real eigenvalues seen in other bifurcations. Here, we're using the analogy of an asymmetric double well potential to illustrate what happens in time crystals during bifurcation. In this analogy, the two wells represent different states of a system. As a key parameter changes, the system experiences a bifurcation, transitioning from a non-oscillatory state to a periodic state. This is very similar to how time crystals shift from a non-time crystalline state to a time crystalline state, where they break time translation symmetry and begin oscillating in a periodic manner. In conclusion to the string time crystals Part 1, let's discuss the log-normal distribution in the biquantum realm state, particularly in the context of modeling time crystals and bifurcation quantum oscillators. Figure 2D from Dicapoltsev et al.'s study gives us an important insight. It shows a log-normal distribution of the power carried by electromagnetic radiation as a function of the radiation angle. What's interesting here is the strong alignment between the analytic calculations and FDTD simulations, which demonstrates the precise prediction of the log-normal emission pattern in photonic time crystals. This not only validates the theoretical model but also confirms that the simulations accurately capture how light emission is influenced by medium modulation in these systems. Thank you all for your time and interest.